From a distance, 3I-ATLAS appears to be a comet, a glowing traveler tracing the edge of our solar system. But as scientists look closer, its metallic shine, strange tail, and chemical fingerprints suggest something far more complex. Is it ice, metal, or a relic from another star entirely?
Was this trajectory designed by some intelligence? Is it a spacecraft or a rock? We can tell the difference if we had enough data.
Today, we explore the mystery behind 3I-ATLAS. The classification problem. In astronomy, names matter. They define how we think about the unknown. But every so often, the universe throws something at us that breaks every label we've built. 3I-ATLAS is one of those things. Ask 10 astronomers what it really is, and you'll get 11 answers. Some say comet, others asteroid, and a few whisper, it's something entirely new. A visitor that refuses to fit inside our neat little boxes. Space, after all, doesn't care about the labels we invent. Traditionally, comets are icy wanderers, frozen gas and dust that flare up as they near the sun, leaving those iconic glowing tails. Asteroids are their opposite, solid, metallic, the leftover bones of planet formation. But 3I-ATLAS, it behaves like both. And neither. From the start, its light signature made no sense. It glowed too brightly for its size, wrapped in a misty halo of dust. Classic comet behavior. Yet the pattern of that glow didn't match anything we've seen before. Hubble's data hinted that its solid core might be far smaller than its light suggested, as if the brightness itself were exaggerating its true scale. That's when scientists reached for a new label. Exocomet, a frozen relic from another star system. But even that didn't quite fit. Some think it's a spent exocomet, long stripped of its ices, now only pretending to act like one. The ghost of a comet still wearing its old disguise. And that's what makes it fascinating. In astronomy, the lines blur constantly. A comet that loses its ices becomes asteroid-like. An asteroid that hides volatile materials can suddenly breathe like a comet. 3I-ATLAS lives right in that gray zone, the cosmic no man's land between ice and iron. So when scientists argue over what it truly is, the answer might simply be all of the above. Nature doesn't care for our categories. It only leaves mysteries for us to chase. And 3I-ATLAS might be the universe's way of reminding us that discovery begins where definitions end. Against the solar wind. Every strange object has a moment that flips the story. And for 3I-ATLAS, it was the way it breathed. Once astronomers accepted that it might blur the line between comet and asteroid, they turned to its behavior. That's when the mystery deepened. Normally, when a comet nears a star, sunlight heats its icy surface. Gases vaporize, dust lifts off, and a glowing tail streams away from the sun. It's predictable, cosmic clockwork. But 3I-ATLAS didn't follow the script. Spectrographic data showed it was outgassing, releasing vapor. But some of that vapor was moving toward the sun instead of away from it, forming what astronomers called an anti-tail. And this wasn't a photographic illusion or a trick of perspective. The material was genuinely being pushed against the solar wind. That discovery turned heads across the astronomical community. Was this a quirk of physics or something hidden within its chemistry? The gases coming off 3I-ATLAS were familiar carbon compounds and trace metals, but in ratios no one had seen before. It was like hearing a familiar melody played in a brand new key. Some researchers proposed that cosmic radiation had hardened its crust over millions of years of interstellar travel. When sunlight struck it, trapped gases may have exploded outward through random cracks, a cosmic pressure cooker venting unpredictably. Others suggested the surface itself might be chemically uneven, layered from its ancient orbit around another star. As more data came in, the puzzle only grew. The vapor trails didn't match the expected rhythm of solar heating. They pulsed, lagged, and erupted unevenly, as if the object were reacting selectively to light. Natural? Sure, but remarkably deliberate. That's when the theories began to splinter. Some scientists suspected a partially metallic core, one that absorbed and released energy differently. Others thought it was shedding fragments of ancient material, remnants fused in the frozen dark between stars. Whatever the truth, one fact stood out. 3I-ATLAS was behaving like no comet ever had. Its outgassing wasn't random. It was patterned, layered, almost alive. And that led to the next, even stranger question. If it acts like this, what exactly is it made of? The missing iron mystery. As data from telescopes poured in, scientists noticed something deeply unsettling about 3I-ATLAS. The object was releasing gases rich in nickel, a metal that forms in the dying stars. But where there's nickel, there should also be iron. That's how nature works. Yet 3I-ATLAS seemed to have misplaced most of its iron. Under normal circumstances, iron and nickel are inseparable cosmic twins. They're born together in supernovae, fused in the final violent breaths of massive stars. When meteorites fall to Earth, their metallic cores almost always show the same story: far more iron than nickel. It's the universal signature of stardust forged naturally. But with 3I-ATLAS, that ratio was flipped, or at least heavily distorted. At first, astronomers assumed a simple detection error. Maybe the spectral lines for iron were too faint, hidden under layers of dust or mixed with gases we couldn't yet separate. But as more readings came in from high-resolution instruments, the pattern held steady. Strong nickel, weak iron. The universe doesn't often hand out coincidences like that. So, what could make an interstellar object rich in nickel but poor in iron? One theory points to chemistry shaped by deep space aging. Over countless millennia drifting between stars, the lighter, more reactive elements might have been stripped or buried, leaving nickel-rich alloys exposed. Another theory suggests something more local. Perhaps it originated in a region around a star where iron condensed differently, producing metallic ratios we've never observed up close. There's also a subtler possibility. The iron is there, but locked beneath a layer that reflects or absorbs in ways our instruments can't yet detect. That's where Mars orbiters and other spacecraft come in. When they begin measuring 3I-ATLAS's heat signature and reflectivity, they may reveal whether that iron core is simply hidden under a metallic shell. This question matters because it tells us how 3I-ATLAS fits into the cosmic. If it's iron poor, it might not be a traditional comet or asteroid at all, but something older, a remnant from a different kind of stellar nursery. The missing iron mystery isn't just a chemistry problem. It's a clue to the object's birthplace. Somewhere out there, around a long-dead star, matter came together in a way that defied the usual rules. And 3I-ATLAS may be the only surviving witness. The blurred line between comet and asteroid. The more researchers studied 3I-ATLAS, the more they realized they were chasing a definition that didn't exist. Every observation blurred the border between comet and asteroid. Two words that once seemed so clear-cut, now collapsing into each other like colors, mixing on a cosmic palette. In theory, comets and asteroids should be easy to tell apart. Comets are icy, fragile wanderers that flare up when sunlight hits them. Asteroids are solid, rocky leftovers of planet formation. But in practice, the universe doesn't respect those boundaries. It recycles and reshapes everything it touches. When a comet loses its ice after thousands of close passes around a star, it doesn't vanish. It hardens. The outer layers bake and darken, leaving behind a rocky skeleton that behaves more like an asteroid. And the opposite can happen too. Some asteroids hide frozen materials deep inside, trapped since the solar system's birth. And when exposed to heat or impacts, they suddenly release gas and dust like a comet waking up from hibernation. That in-between state has a name: transition object. And 3I-ATLAS fits that label perfectly. It moves like a comet, sheds material like one, but its spectral fingerprints suggest a tougher metallic surface, more asteroid than ice ball. It might be what scientists call a carbonaceous hybrid, a body made of metal-rich rock coated in remnants of volatile dust. What makes this fascinating is how it changes our picture of interstellar travelers. A comet that's been wandering between stars for millions of years would have endured radiation, collisions, and freezing temperatures beyond imagination. Over time, its soft ices would erode away, replaced by layers of carbonized minerals and heavy metals. The result? A body that looks like a comet but behaves like a relic of planetary debris. The ghost of a world that once was. Some researchers have started calling such objects rogue comets, much like rogue planets. They've been kicked out of their home systems and drift endlessly through the galaxy. They aren't bound to any star, only gravity itself. And that's likely where 3I-ATLAS belongs. It's a survivor of cosmic exile, a hybrid object that defies simple classification. Whether it began as an icy wanderer or a metallic fragment, time has stripped it down to something unique. A messenger from the space between systems, carrying the signature of a world we'll never see. The tail that points the wrong way. By the time scientists had wrapped their heads around 3I-ATLAS being a hybrid between a comet and an asteroid, something even stranger appeared: a tail that pointed the wrong way. When early telescope images were analyzed, astronomers noticed an optical oddity: a faint streak of light extending toward the sun, not away from it. At first glance, that seemed impossible. Every comet tail, without exception, flows in the opposite direction of sunlight because solar radiation and charged particles push the gas and dust outward. Yet here was 3I-ATLAS, breaking the rule again. This backward feature was quickly labeled the anti-tail. Normally, an anti-tail can appear in photographs when dust particles left behind along a comet's orbit line up with our viewpoint on Earth, creating a perspective trick. But that explanation didn't fit this case. 3I-ATLAS's anti-tail wasn't a visual illusion. It was a real active stream of material, physically being ejected against solar pressure. That discovery forced scientists back to the drawing board. One theory suggested that as 3I-ATLAS rotated, heat built unevenly across its surface. Instead of venting gas away from the sun like a standard comet, its crust may have fractured in spots that faced inward, releasing jets that curved backward. Essentially, it could be venting material from a sunlit hemisphere whose internal pressure was misaligned with its spin. Others proposed a more complex answer. Over millions of years drifting in interstellar space, the surface of 3I-ATLAS may have developed a hardened crust rich in metallic compounds. When sunlight hit that irregular coating, it might have caused specific areas to heat and release gas differently, a process known as preferential outgassing. It's rare, but not impossible. It just hadn't been observed on this scale before. What made the anti-tail so fascinating was how it blurred another boundary, this time between physics and perspective. We're watching natural laws play out, but in a way that forces us to question whether we've seen the whole picture. Perhaps rogue comets that have traveled through interstellar space for eons don't behave like the ones born here. The constant exposure to radiation, micrometeorite impacts, and freezing void temperatures may have restructured their surfaces into something almost alien. Not technologically, but chemically. Scientists are watching closely to see if the anti-tail fades as 3I-ATLAS moves farther from the sun. If it disappears, it supports the idea that it's caused by solar heating of an irregular crust. But if it persists, it could signal deeper processes within the object layers that retain energy differently, or even a fragmented core venting from multiple points. Either way, the anti-tail isn't just a curiosity. It's a key piece of evidence showing that 3I-ATLAS operates by rules shaped outside our solar system. And understanding those rules could reveal not just what this traveler is made of, but how interstellar space itself sculpts the worlds that pass through it, forged in a dying star. As the debate over 3I-ATLAS's strange tale unfolded, another revelation emerged, one that shifted the conversation from gases to metal. Beneath the fading coma, astronomers began detecting hints of something solid, something far denser than expected. It wasn't just an icy traveler anymore. Its spectral readings pointed to metallic compounds, and that changed everything. Most comets are fragile, porous, and lightweight, made mostly of frozen gases, dust, and organic material. But 3I-ATLAS seemed to reflect light in a way that suggested a harder, shinier surface. That observation opened a new possibility. Maybe it wasn't just a rogue comet. Maybe it was part metallic asteroid. To understand why that matters, you have to look at how metallic asteroids form. When young planets are shattered by massive collisions, their molten cores, rich in iron and nickel, are exposed. Over time, those fragments cool slowly, and the metals inside crystallize into stunning lattice patterns known as Widmanstätten structures. They're nature's record of planetary destruction, frozen in steel. Scientists studying meteorites on Earth see this story all the time. Iron meteorites found in deserts or Antarctica carry those same crystalline scars. They're slices of lost worlds, reminders that every rock has a violent past. What caught researchers' attention with 3I-ATLAS was how closely its reflective properties matched those same metallic meteorites. It wasn't purely rocky or icy. It had the gleam of something forged in fire. Within those metallic structures are trace minerals rarely seen on Earth but common in space. One of them, schreibersite, is an iron-nickel phosphide that carries an element vital for life, phosphorus. On our planet, this mineral was likely one of the key sources that seeded early biology with the chemicals needed for metabolism and DNA formation. And here it was, possibly being detected again, in an object from another star system. That's where the mystery deepens. If 3I-ATLAS contains metallic compounds similar to our own planetary debris, it might mean that the building blocks of life, phosphorus, nickel, and iron, are universal. But if it's chemically distinct, that could tell us that other star systems create planets and comets with entirely different recipes. The idea that 3I-ATLAS might resemble the metal-rich asteroids we've only just begun to study, like NASA's Psyche mission, adds another layer. Psyche is a world made almost entirely of exposed planetary core material, and studying it will help decode how metals behave in space. If 3I-ATLAS mirrors those readings, it might be our first glimpse at how interstellar metallurgy looks. 3I-ATLAS may have started as a comet, but what's emerging now is something older, heavier, and more valuable. A wandering alloy from a system long gone cold. A metallic ghost, still carrying the fingerprints of a star that once burned light years away. The element that decides who lives. When scientists realized that 3I-ATLAS might contain traces of metallic minerals like schreibersite, the focus shifted from physics to biology. That single compound, a blend of iron, nickel, and phosphorus, opened an entirely different conversation. Because phosphorus isn't just another mineral, it's one of life's most essential ingredients. On Earth, every cell, every strand of DNA, and every molecule of energy transfer depends on phosphorus. It's part of adenosine triphosphate, or ATP, the molecule that powers almost every biological process. Without it, nothing alive could move, grow, or think. But here's the catch. Phosphorus is surprisingly rare on our planet's surface. Most of it is locked deep in rocks or bound in forms that life can't easily use. So how did early Earth get enough of it to start biology in the first place? That question has puzzled scientists for decades, and one of the leading theories points straight to the sky. Billions of years ago, during a period called the Late Heavy Bombardment, the planet was struck by countless meteorites, many of them metallic. When those meteorites weathered in volcanic pools and hot springs, their Schreiber site interacted with water, creating compounds that released reactive phosphorus. In lab simulations, this process even produced pyrophosphate, a molecule thought to be an early energy carrier, a primitive ancestor to ATP itself. In other words, space metal might have jump-started life. Now, when astronomers look at 3I-ATLAS, they see more than an interstellar traveler. They see a potential test case for this theory on a galactic scale. If its composition includes phosphorus-bearing metals like schreibersite, it could help scientists understand whether life's ingredients are scattered evenly throughout the Milky Way, or if Earth's chemistry is a rare cosmic accident. This leads into one of the biggest questions in science, the Fermi paradox. If life is common in the universe, where is everyone? Maybe the answer lies in the chemistry of worlds, not their location. If certain star systems form with low phosphorus levels, they might never produce biology at all. Their planets could stay sterile forever, not because they lack warmth or water, but because they simply don't have the right spark to power life. By sampling interstellar objects like 3I-ATLAS, scientists could begin mapping the galactic distribution of phosphorus, identifying where the universe is chemically fertile and where it's barren. If we find that phosphorus is unevenly spread, it might explain why some worlds bloom with life while others stay silent. So this isn't just about one comet-like object anymore. It's about finding out whether life is a universal accident or a cosmic inevitability. And if 3I-ATLAS carries even a trace of that same life-starting chemistry, it's more than a wanderer. It's a messenger from a star system that may once have had its own version of us. The identity crisis. After months of observation, 3I-ATLAS has forced astronomers to confront an uncomfortable truth. It doesn't fit the rules. Every time a box is drawn around it, comet, asteroid, metallic fragment, it slips right out. The evidence now points to something that might be both, or perhaps neither. On paper, it behaves like a comet. It has a coma, a faint tail, and visible outgassing. But the composition tells another story. Metallic surfaces, nickel traces, and a density that doesn't match typical icy wanderers. It's as though nature took the body of an asteroid and wrapped it in the behavior of a comet. Some researchers have begun calling it a cometoid, a transitional object shaped by time, radiation, and exile. The idea is that interstellar space acts as a cosmic forge, baking away volatile materials while leaving the dense metals behind. Over millions of years, what began as a bright, icy traveler becomes something tougher, darker, and far stranger, a hybrid object that carries scars from two very different worlds. Others argue that 3I-ATLAS may represent an entirely new class of celestial body, an interstellar metallic hybrid. These are objects that once orbited alien suns, ejected during planetary collisions or system disruptions, then drifted for ages through the galactic dark. By the time they reach us, they've been stripped, hardened, and reshaped beyond easy classification. Even the way it reflects sunlight hints at a surface unlike any comet we've seen. Too reflective in some areas, too dull in others. That suggests patches of exposed metal or mineral crust mixed with older carbonized dust. It's a chaotic blend, but chaos often hides the truth. So, is 3I-ATLAS really a comet? Or has it evolved into something entirely new? a survivor of cosmic erosion, a metallic ghost from another sun. Perhaps the real mystery isn't what 3I-ATLAS is, but what it represents. A glimpse at how the universe blurs every line we try to draw. And as it moves farther from Mars, slipping once again into the black, one question remains. Are we seeing the past of a comet or the future of a new kind of world? The ongoing investigation. As 3I-ATLAS drifts farther from Mars and heads deeper toward the inner solar system, the mystery surrounding it only grows thicker. The world space agencies may not agree on what to call it, but they all agree on one thing. This is an opportunity we can't afford to waste. While NASA remains quiet during its government hiatus, other missions are picking up the slack. The European Space Agency, China's National Space Administration, and the United Arab Emirates have all directed their Mars orbiters toward 3I-ATLAS. These orbiters weren't designed for deep space tracking, yet their instruments can still gather valuable readings, measuring brightness changes, thermal emissions, and the faint spectra of gases leaving their surface. Even the Mars Reconnaissance Orbiter, MRO, famous for its high-resolution imaging of Martian terrain, has joined the effort to help estimate the true size of the object's nucleus. The goal is simple but monumental. Determine what 3I-ATLAS really is before it vanishes back into the dark. By combining orbital data, light curves, and infrared readings, scientists hope to map its shape, density, and composition. If the readings confirm a dense metallic structure, it could validate the idea of an interstellar hybrid, an object forged in another star system and preserved by the cold between galaxies. Meanwhile, the JUICE spacecraft, currently en route to Jupiter, will attempt long-distance observations as 3I-ATLAS crosses its path. It's a rare alignment, one chance for multiple spacecraft to collect synchronized data across millions of miles. The information won't give us glossy close-up photos, but it could settle the ongoing debate about size and reflectivity. Is it a massive metallic fragment glowing under sunlight, or a smaller body wrapped in a cloud of reflective dust? Researchers are also developing computer models that simulate how 3I-ATLAS might have evolved. These models trace possible origins, from a shattered moon orbiting a distant star to the ejected remains of a planetary collision. The anti-tail, the missing iron, and the unusual nickel ratios are all being used as clues in this digital reconstruction. Every scenario leads to the same humbling realization. Our solar system isn't unique. The same cosmic chaos that shaped us is happening everywhere. In the coming months, as new data trickles in, scientists expect to release refined measurements that could either confirm its metallic core or rewrite the entire case once again. Whatever the result, 3I-ATLAS has already achieved something remarkable. It's forced us to rethink how we define the objects that drift through space. Because maybe this was never about proving whether 3I-ATLAS is a comet or an asteroid. Maybe it's about acknowledging that the universe builds more than categories. It builds stories. And 3I-ATLAS is one of them. A silent traveler carrying the fingerprints of another world, now passing through ours. Thanks for watching. If you enjoyed this deep dive, make sure to like, subscribe, and share. What do you think lies in this mystery? A comet, an asteroid, or something entirely new? Drop your thoughts below.